Hello and welcome to the first day of nuclear physics. The first big question we really want to be asking ourselves is mass always conserved?
Homer, where are you going?
Work.
It's 4 o'clock on a Saturday.
I have to count the atoms at the nuclear plant. Conservation of mass, it's the law.
Well, according to Homer, it looks like mass is always conserved. Now, let's talk a little bit about the structure of an atom. You should remember from chemistry that we've got protons and neutrons that make up the nucleus of an atom, and the electrons that swirl around it. We like to think of them as orbiting, even though we know that that's not completely true now. But physics, at least in this unit, we really want to focus on the nucleus. That's hence the name nuclear physics, right? So all nuclei are made of protons and neutrons, okay? And both of those together, we call those nucleons. So protons and neutrons are both considered nucleons. Now the atomic number, abbreviated Z, is the number of protons in the nucleus. The neutron number, N, is the number of neutrons in the nucleus. And the mass number, which is abbreviated as A, is the total number of nucleons. So the protons and the neutrons added up together. Now the notation that we typically use when dealing with these elements is the form here that you can see. The X is the element symbol, and then A is the mass number, and Z is the atomic number or the proton number. So we can see an example here with helium. What is interesting is that we will frequently actually omit this bottom number here, the 2 for helium. The reason for that is because we know that every helium atom in the universe has 2 protons. That's what makes it a helium. Every lithium atom has 3 protons. So it really is redundant to have that number. But the number of neutrons can be different, right? And that is an isotope. So atoms that are the same element but have a different number of neutrons are called isotopes of each other, right? So the same number of protons but different number of neutrons. So for example, we have 3 different variations of the hydrogen atom. So this hydrogen atom has just 1 proton and 0 neutrons. This one has 1 proton and 1 neutron. And this has 1 proton and 2 neutrons. So the natural abundance of the isotopes can differ substantially. So for example, the helium-1 is vastly more common than the helium-2 and helium-3. I think, I need to look it up, something like over 90-something% of the helium atoms are H1. So what we like to do is when we talk about the atomic mass of an atom, that is the weighted average of all of the isotopes. Meaning, if these are the only 3 hydrogen atoms in the universe, we don't just say 1 plus 2 plus 3, divide it by 3, we get an average of 2, because the vast abundance of hydrogen in the world is H1. So it's weighted more towards the one, so that the actual mass, I forget what it is, 1.01 something, 1.02 something. So it's a weighted average. So the more abundant a specific isotope is, the more that shifts the mass in its favor, the average mass. Now let's talk a little bit about charge and mass of these subatomic particles, right? Protons, you know, have a positive charge. The amount is 1.602177733 times 10 to the negative 19th coulombs. No, you don't need to memorize that. I'm going to give you that number. A coulomb is the unit for charge, and we'll talk about electricity in a couple of units, and we'll learn more about what a coulomb actually is. Electrons have the exact same amount of charge, just opposite in sign, right? Electrons have a negative charge, protons have a positive. And then, of course, neutrons, as we know, are neutral. They have. And looking more at the masses, we see that the protons and neutrons are significantly more massive than electrons. I mean, they're almost 2,000 times more massive. And then the actual value of the mass is listed here in the bottom. Of course, you know what kilograms are, so we can see that this is a really small number, 10 to the negative 27th. That means there's 26 zeros in front of this one. Right? This right here, AMU, stands for atomic mass units. So protons and neutrons are about 1 atomic mass unit. We'll talk more in depth about these units, but these units, when dealing with nuclear physics, are extremely convenient to use. So even though it's a new unit and you might feel like, oh, it's new, I don't like it, it's actually going to make our lives very, very easy, and we're going to love those. Now here's a really interesting fun fact. Because the rest energy of a particle is given by E equals mc squared, you guys have seen that equation before, right? Einstein's famous equation, E equals mc squared. What that's saying is that energy is related to mass times the speed of light squared. C is the speed of light. So it's often convenient to express the particle's mass in terms of its energy. And this conversion factor right here is going to be very, very helpful, okay? So 1 AMU is equal to 931.5 mega electron volts per C squared. Now, that might look kind of confusing right now because like a mega electron volts and a what? But I promise we'll go through this in detail, and this number is going to make your life easy and wonderful. So in that E equals mc squared equation, C is the speed of light in a vacuum. We are going to use the number 3.00 times 10 to the 8th meters per second. Now for now, even though you don't really know what an electron volt is, and we'll talk more about that when we get to electricity and magnetism, but what you need to know is that 1 eV, 1 electron volt, is 1.6 times 10 to the negative 19th joules. And you know joules, that's energy. So 1 eV isn't a very big amount of energy, right? And then M stands for mega. Mega is 10 to the 6th. So a mega electron volt is 1 times 10 to the 6th electron volts. Let's talk a little bit about nuclear stability. Now protons, with them being positively charged, like to repel each other. So the big question is, why doesn't the nucleus just fly apart, right? If all of those protons are so close and the Coulombic force is repelling them, how do they stick together? And that is because of the nuclear force, which is the strongest force in the universe. It is an extremely strong, attractive force, but it only works over really, really tiny distances. Once those protons get slightly farther away from each other, right? I mean, 2 femtometers is really, really small. Then the Coulombic force becomes much bigger than the nuclear force, and those protons are repelled by each other. The protons attract each other through that nuclear force and repel each other through the Coulomb's force, or Coulombic force. So the nuclear force associated with a proton-proton or a proton-neutron or neutron-neutron interactions, right, any two nucleons is what we're saying, are about the same. And for the sake of our class, we're going to say that the nuclear force is the same between any two nucleons. The only difference is that that Coulomb force for the proton-proton interaction makes that net force just a little bit smaller. But for the sake of our class, we're going to kind of just say it's the same no matter. Now, if we wanted to figure out just how stable that is, right, if we get too many protons together, will they break apart and fly apart? So if we did a plot of n versus z, right, the number of nucleons versus the number of protons, then we see this. Now, this red line is the 1 equals 1, right? If n equals n line right here. And then the blue dots represent the number of protons versus the number of neutrons. So early on, we can see that the blue dots are pretty much identical to the red line. So for smaller atoms, up to about 20 protons, right? So anything up until, about potassium or calcium in that area, they tend to have a 1-to-1 ratio for protons and neutrons. But as the atoms get significantly larger, you can see it requires more and more neutrons versus protons to be able to keep that element stable. And then 80 is generally considered the last really stable element. After Mercury, about there, right? There's some gray area here, but after Mercury, the atoms become too big and they're unstable. And everything above that is going to be radioactive because it's too big to be stable. So like this says, I guess this is what I said before, but early on, right down here in the lower range, it's about equal numbers of protons and neutrons. Now, this is because as the number of protons increases, the strength of that Coulomb force increases, which tends to break that nucleus apart. More neutrons are needed, right? It's kind of like a little bit of glue, right? And although that's a terrible analogy because it is possible to have too many neutrons, but generally speaking, the more neutrons you have, the more stable it is, unless you go overboard. But it's kind of like that glue that holds those protons apart. Now let's talk about one of my favorite topics with nuclear physics, this idea of binding energy and something called mass defect, which is a little bit strange. Mass defect is that the total mass of a nucleus is always less than the sum of the masses of the nucleons. And so that difference in mass is known as the mass defect. So what does that really mean? Okay, so I've got 1, 2, 3, 4, 5, 6, 7 nucleons right here, 3 protons and 4 neutrons. So if I weighed each of these separately and added it together, I would get some number, right? 7 point something AMU. But once we add them all together, and we've got this nucleus here, and we weigh it, we would find that the total mass of this nucleus is lower than the mass of those 7 things individually. It's a strange phenomenon that kind of perplexes people early on, but you kind of get used to it once you understand the idea of binding energy. To get all of these subatomic particles together and bind them, it requires energy. So when you fuse things together, energy is released. And we saw that equation, E equals mc squared. So that energy that's released is the mass difference, that mass defect. And this is basically what we just said, right? Because mass is another manifestation of energy, the total energy of the bound system is less than the combined energy of the separated nucleons. That's because that binding energy is released as they're bound together. So the difference in energy is called the binding energy. The difference in mass is called the mass defect. They're one and the same, right? Binding energy and mass defect are the same thing, but we're referring to it with different units. The mass will be in AMUs and kilograms. The binding energy will be in joules or mega electron volts. But it's the same phenomenon. So the binding energy is equal to the mass defect times c squared. But you'll see with the units mega electron volts, the c squared cancel out. Let's try a little sample problem and figure out how to solve these. And I think I should be able to write on this. Please tell me that this is working correctly. It is. All right, so the most abundant isotope of helium has a 4,2, or a helium-4 nucleus, whose mass is 6.6447 times 10 to the negative 27th kilograms. For this nucleus, find the mass defect and the binding energy. Okay, well, to find the mass defect, what we need to do is just see what is the sum of all of the parts. So it's a helium, which means it has 2 protons, and it's a helium-4, so that means 2 protons and 2 neutrons. So if we go back to the previous slide, I have it here in my notes, so I don't need to go back. But if you go back, you can see the mass of each of those protons and neutrons. So I've got 2 protons, and I'm going to multiply it by their weight, which is 1.6726 times 10 to the negative 27th kilograms. And I'm going to add 2 neutrons, which is 1.6750 times 10 to the negative 27 kilograms. So when we add those up, we get 6.6952 times 10 to the negative 27th. It's a little bit sloppy there. Okay, so the sum of the parts is this value right here. But it tells us that the actual mass is this. So to find the mass defect, all I need to do is subtract these 2 numbers. So 6.6952 times 10 to the negative 27 minus this value, and I'm going to end up with 5.05 times 10 to the negative 29th kilograms. Right? All I did was I subtracted this value here, right? I added up all the parts, and then I subtracted the actual mass, and that gave me the mass defect. Now, to get the binding energy, we use our E equals mc squared equation. So I'm going to plug in my mass defect to get the energy is equal to 5.05 times 10 to the negative 29th times the speed of light squared, which is 3 times 10 to the 8th squared. Now when you plug this into the calculator, I want to remind you when you're using the scientific notation to put parentheses. Otherwise you might just square the 8 or square the 10 to the 8th and not square the 3. But when you do that, we should get an answer of, let me look at my notes here, 4.55 times 10 to the negative 12th joules. But notice it's asking we want it in joules and in mega electron volts. Okay, how do I convert to mega electron volts? Well, remember to do our unit conversions, we've got the 4.55 times 10 to the negative 12th joules. So I want to convert from joules into electron volts. We know that 1 electron volt is equal to 1.6 times 10 to the negative 19th. And that will give me electron volts, but I want mega electron volts. So 1 mega electron volt is equal to 1 times 10 to the 6th electron volts. So that means electron volt will cancel with electron, joules with the joules, and that leaves me with the mega electron volts. I multiply across the top, I multiply across the bottom, and then divide those two, and that will give me an answer of 28.4 mega electron volts. This is a pretty intense problem. This is, whew, that was intense. Let's try problem number 2. Actually is going to sound really familiar. The atomic mass of this is 4.0026 AMU. Using atomic mass units instead of kilograms, obtain the binding energy of the nucleus. This is the exact same question as before, but we're just going to use different units. And the reason I'm doing this the exact same is because I just want to show you how nice these new units are. And I don't have a whole lot of space to draw on here. Had I thought through it a little bit better, I would have given myself a lot of space. So I'm going to write on top of the diagram right here. But the mass defect, I take this mass and I subtract this mass. So taking the 4.033 minus 4.0026, we end up with, I'm just going to say mass defect is equal to 0.0304 AMU. Now, remember that 1 AMU is 931.5 mega electron volts per C squared. Notice what happens if I want to find the energy. Energy is equal to mass times C squared. Well, if I convert this number into that mega electron volts per C squared, watch what happens, right? So let's do that. 0.0304 mega electron volt, or excuse me, AMUs. And now I need to multiply by 931.5 MeVs per C squared over 1 AMU. And that is going to give me 28.3 mega electron volts per C squared. Now this looks kind of confusing, like, well, I just want energy, not a per C squared. But once we plug this in right here, notice what happens. This is amazing. E equals 28.3 mega electron volts per C squared times C squared. Oh look, that just cancels out and becomes easy. So oftentimes what happens, I'm going to be honest, I kind of get lazy and cheat. I'll try to be really good, especially at the beginning of the unit, and go through every step. But usually when we're doing the conversion, I don't even like remember the over C squared that we have right here. I usually just go straight from AMU into mega electron volts and just drop the C squared because I know that it drops anyway once I plug it into the equation. So I get this. So 28.3, the previous problem we got 28.4, that's just a rounding error from rounding these numbers, but we get the exact same answer using the two different ways. But notice that this math is a lot easier to use for a couple of reasons. Number one, it simplifies the E equals MC squared, but also we're not dealing. So this is just practice. I've actually already given you the answer here so that you can confirm that your answer is correct. So you can pause the video now, read through this, and try it on your own. I'll count to 5. Great, and now you can go on to the next problem. Okay, and again, I've already given you the answer down here on the bottom, so you can just try this one all on your own to make sure that you can get it, okay? So pause this video because I'm about to end the video right now. Pause it, and you have time to solve this, but have a wonderful day. I'll see you guys later.